I attended a meeting very much like this about 15 years ago. We were starting to develop the R language, and at the time we said, well, maybe a couple hundred people will end up using it. Recently, the number of users is estimated as being several millions. Roger Payne and others have had Coursera courses on R programming and reproducible research and things like that have attracted over 1 million users, or 1 million people at least signed up for it, download the software, type 2+2 and enter. So I have a long history with R and before that with S, predecessor language. And I have been often trying to do things fitting some models that were kind of compute intensive. And if you do this, you know that you're going to have to go into the two-language parallel. You're going to have to write some code and compiled code, and then you're going to have the interfacing between those. And it's the same whether you're working in MATLAB or whether you're working in Python or whether you're working in R. And I guess before the famous Valentine's Day announcement, sometime it would have been around the end of 2011, early 2012, I was looking at CLang and checked the LLVM website, and they mentioned this technical language that was using the LLVM just-in-time compiler. And so I started looking at Julia. And the more I looked at it, the more I thought, this is really where things should be going. So John and I were discussing on the way out to lunch which of us was going to have less technical talk. And I think I'm going to win. But my rationale on this is to say that languages like Julia start off with the technical part, but they can end up with people who are much less technical using them or using packages written. And so you have to be aware of them. And kind of echoing a comment that Alan made before lunch, that you think of linear programming problems, and of course it's based on a matrix, and you take this matrix and you do things, and so just understanding that, well, there's a higher level at which you can think about this. And it was similar with Madeline's talk, trying to say, okay, we'll look at optimization problems and move it up. Now, I'm going to talk about a much, much simpler sort of situation. And I'm sure many of you endured an introductory statistics course. And a characteristic of that, unfortunately, is that it's often taught as a series of formulas. And the formulas were derived in the days when you had to do every calculation by hand. So the formula becomes very opaque. It's designed to cut down on the number of additions that you need to do by hand. And you end up with these very opaque ideas, which are actually quite simple, but they've gone to great lengths to disguise them. So I'm going to try to talk about what seems to be a horribly simple idea. In statistics, we'll talk about the observed response as being a random variable. Right? And I'm going to drive you crazy because I refer to the number of observations as m and the number of coefficients or parameters as p. So my matrix X is going to be n by p, it's not m by n. I'm sorry, I can't talk about m observations. So in a general sense, this idea of the linear predictor says that you're going to have a distribution for the response, and it's going to depend upon this model matrix times a coefficient factor. And we refer to that as the linear predictor. It's often written as eta. And the elements of the coefficient vector are parameters that are to be estimated, and X is the known and fixed model matrix. of the, depending upon the observed values of covariates, if you speak machine learning, their features. Now, the computational methods are usually described starting with x and y. And regrettably, people don't have much of a background in numerical linear algebra, so they do x transpose x inverse x transpose y. And, you know, I run screaming from the room every time I see R code that is a literal translation of that calculation. So, it's fairly easy. I mean, you could do this in Julia. All you have to do, this is just generating a response for a simple linear regression. You put a vector of 1s on the beginning, you put the vector x, you use the backslash operator, and it's done. Right? And then the statistician says, but I want more. I don't just want coefficient estimates. That's what we call a point estimate. We have to know something about the variability. There's variability in the data. We have to know something about that. And you know, I want to know all these other crazy things like how the variance is decomposed in analysis of variance. Or I actually want to use this in terms of a generalized linear model, logistic regression, Poisson regression, and so forth. And they're going to involve this link function and weighting and all of those kinds of things. But the basic least squares calculation is central to a very large number of statistical models. And you say, well, first of all, I want to sometimes do and often do something more than just get beta hat. And there's an implicit assumption here that the columns of x are the easy thing. You know, it's just sort of, that's your model. The ecologists who take my introductory courses, or the people in psychology and sociology, they don't want to think about matrices to begin with. And they don't want to decide how to fill out all of those columns. So it goes a little bit beyond that for us some of the time. Now, I mentioned that you probably took an intro stat course, and you may have seen some of these words, you know, t-test, pair t-test, one-way, two-way, et cetera, analysis, variance, analysis, covariance, interaction terms, logistic regression, et cetera, et cetera. Mixed effects models happens to be where I spend my time, but we're going to look at a more general sequence on this. And these can all be expressed in terms of either a least squares calculation or in terms of iterative least squares calculations, or in some cases penalized calculations. And if you looked at something like the Elements of Statistical Learning by Hasty, Tipsheroni, and Friedman, or their Introduction to Statistical Learning, which is two other authors, Hasty, Tipsheroni, and I forgot their names. Half of the model types that they describe there have a least square, have a calculation like this in heart. But the trick is, how do I go from a high-level description of the model to that X matrix? And it's surprisingly subtle. Right? So this is why it's not a high-level talk. I'm not talking about how you get general optimization problems and express them compactly. I'm simply saying, I want to think of, I'm going to incorporate these variables in this way, and how is that going to generate a model? Now, you know, that doesn't seem like much. I've worked with people who, for whom those X matrices are millions of columns and tens of millions of rows. And you don't want to have to specify every one of those millions of columns by hand. You have to do something a little bit more effective than that. And the big thing is that not everything that you work with is just a numeric value. You often have categorical covariance. I don't know what the term is in features, but the idea here is you're not expressing that it's a measurement of some sort. You're expressing that it's of this type. You know, it's the treatment group, the control group, treatment 1, 2, and so forth. Or you're saying that, you know, this is the subject who was measured. This is the item that they were responding to, or something along those lines. So there's a lot of mixing and matching of these. But categorical covariance is where it starts to get interesting. In the data frames and data arrays packages for Julia, these are represented as a pooled data array. John's going to talk about the data frames in a few minutes. So the point about the categorical covariant is that it generates a group of columns. It doesn't just generate one. And the contributions often end up not being of interest. You're not, the coefficients themselves are not the thing that you're interested in. They're sort of a secondary piece of information. You're interested in what's the overall contribution of this term in explaining the variability in the data in some general sense. Now, it turns out that the geometry and the algebra are fairly simple for this. And now the computation is also simple, but not when the techniques were formulated. So this is where things get into trouble, because the techniques were formulated, I can't even remember, around the beginning of the 20th century. I think Gossett wrote around 1909 and Fisher wrote around 1913 or something like that. And computation was a little different then. But these were clever people, Fisher in particular, and so he found ways to simplify the calculations in certain highly structured situations. Now what I'm going to tell you is that this is all about generating orthogonal subspaces in the response space and projecting the response onto those spaces. Right? He understood that. He didn't want to have to try to tell the agronomist that, oh, you just work out this projection. So what he did was he said, okay, here's a table, and you plug the numbers into this table. And the vast majority of people who take statistics are not going to learn about models. They're going to learn about formulas. And they still learn those damn formulas from 1915. And then they try to generalize them. So they think of it as it's just a formula. And you might have learned those messy formulas that are completely irrelevant today. But if you're going to learn it as a rote calculation, you think that's the end. That's where I'm going.
What kind of calculations are you talking about?
Oh, the analysis of variance tables and et cetera on this. If you ever look at my area, people talk about expected mean squares and observed mean squares and so forth. It's just dumb. There's much simpler ways of thinking of it. So we'll assume if we're just going to fit something by linear methods, then we're assuming that there's this Gaussian distribution in the background. That sigma squared I there is referring to the variance covariance matrix, and we refer to that as a spherical distribution because the contours of constant probability are spheres. So the probability model is intimately linked to geometry. Distance is the metric, right? The Euclidean distance. And so if you want to get the maximum likelihood estimates, you find the parameters that are going to give you the greatest probability density. And since everything's involved with distance, you're just minimizing the distance between the fitted value and the observed value. Now, if you know about the QR decomposition, then you can write X as a product of Q times R. Q is actually a virtual matrix. It's the same size as X, or it can actually be considered as the full n by n matrix, but it satisfies this orthogonality condition. And it's very good, from the point of view of numerical linear algebra. It has condition number of 1 and all that sort of stuff. And this is an upper triangular matrix. And as I said, we talk about n by p. So this would be a p by p upper triangular. And the fact that this is an orthogonal matrix means that it's distance preserving. So you can multiply everything in here, and you end up with a system to solve, which looks like that. And you're all good as long as you have full column rank. You don't. So then you have to start figuring out what you're going to do. So the idea is that you want to go from a high-level description, you want to produce a model matrix like this, and you want to get it in such a way that you're guaranteed to have full rank, or most of the time guaranteed to have full rank. The other thing about it is that, well, frequently, I said you're not always interested in the category, in the coefficients. I guess it's back here. This vector is called the effects vector. And frequently, that's the answer. You don't even care about what the coefficients are. Because this has taken that response and it's applied a orthogonal transformation to it, observably. But now the components correspond to the categorical covariance, or they correspond to interactions or other terms that are meaningful to the experiment. So really, by the time that you've applied the orthogonal transformation to it, you just need to start looking at that transformed vector. You know, sometimes you want that also back at the coefficient stage. So the categorical covariance, as I say, if you have a covariance, a treatment, you know, there might be 3 or 4 levels of it, so you're going to generate 3 or 4 columns that are indicators of that treatment. You got a 1 in the first column if it's the control group, and zeros otherwise. You got a 1 in the second column, that's treatment 1, and zeros otherwise, and so forth. So you could go ahead and you could put those in. We also have what we call interactions and so on. And the number of elements in each section is the degrees of freedom. And when I first took statistics, I thought, that's interesting. That's the same thing that people refer to about the dimension of a subspace. And that's not an accident. It is the dimension of a subspace. It's just not ever taught that way. So it is the dimension of a linear subspace. And the simple way of generating that group of columns is to use the set of indicators. But if you're also going to have a column of 1s in there, you're going to end up with a rank deficient matrix. Because if you add up indicators, you end up with a column of 1s. And if you have more than one term of this nature, you're going to end up with 2 sets of columns, each of which would add up to 1. So even if you don't have the constant term in there, you're still going to get rank deficiencies. So you have to be careful about the rank. Now, there's different ways of doing this. We can include all the columns, check for numerical singularity, and adjust. And that's the technique that's used by many popular old-style statistical packages. SAS comes to mind. Jim Goodnight, who was one of the people who founded SAS and is considered the richest person in North Carolina, he came up with a method involving pivoting, I forget what it was, for solving such a rank deficient system when he was a graduate student, and it to this day is used in SAS, 40 years later, because nobody wants to go up and say, by the way, Jim, this is really a terrible way of doing things. He's the boss. It's a privately owned. But it's the toast and then scraping approach. All right. So you make it bad and then you try to recover. If you take any linearly independent set of, you started out with k columns. If you take any linearly independent set of k minus 1, then you can generate those. Now, these go by the name of contrasts because they compare one level against another, or something along those lines. Technically, what we use for contrasts a lot of time isn't really contrasts, but that's because there's a further technical definition of what contrasts. For definiteness, you can drop the first one. That works all the time. So if you want a definite method of doing things, you just drop the first one and you end up with something that's called treatment contrasts. Other times, we may choose another set such that, for example, they are orthogonal to each other and they are orthogonal to the constant column, and that's going to improve stability of the calculation. Or because they provide a convenient interpretation of the coefficients. And this gets a little subtle, actually, because a lot of the time, it's not these coefficients that you're interested in, but it's what they induce in the interpretation of the intercept. Another approach, which is getting into these very large problems. So, my classic example is I work with people who analyze the annual test scores of students that are mandated by the No Child Left Behind Act. And in that case, depending on the state, by now you could have tens of millions and possibly hundreds of millions of test scores. And you have seen over the years many, many students into the millions. So you don't want to start throwing a million columns in there without some kind of regularization. And that's the analysis point of view for what happens with random effects. There's another idea that comes from the probability statistical formulation of it, which is where you're saying that I'm not viewing these students as being completely independent. They're coming from a population. And so I want to relate them to each other. John Tukey used the term, you want to borrow strength. You don't necessarily expect that you have one student here, a whole bunch of people around there, and then somebody way, way out in terms of their ability or their lack of ability. So this is the regularization that comes in. And then interaction. So interactions come up when you try to see, okay, if you change this condition, does it change the response for another condition? And this can get fairly sophisticated in terms of the interaction. So I'm going to talk about the order of an interaction, which is the number of terms, and by extension, if you have the original term by itself, then you're going to have first order interaction, or an order of one, because there aren't any products. And then if you're going to have the constant, that's going to be at order 0. And with few exceptions, sensible models obey a heredity principle, which is that if you've got a high order interaction, it doesn't make sense to try to eliminate that without, have that in the model without having all of its descendants. So if you have A times A interaction with B, interaction with C, interaction with D, you should have all of the subsets of A, B, and C, and D. So we need to be careful when we generate terms. We want to look at them in specific partial ordering. We want to retain the information, the original ordering for terms. I'm not going to use the word order too much here. We want to retain the original sequence for terms that are of the same order. But we want to have all the order 1 terms coming before all the order 2 terms coming before all the order 3. And oftentimes we saturate a model, which means that we look at all the possible interactions. So that's not too bad if you have 2 factors that you're considering, because you're going to end up with a total of 4 terms. But when you have 20, then you're going to end up with 2 to the 20. It's going to go through that. So anyway, there's this formula language, which was used widely in S and R. I think that's where it became the most popular. And the constant term is implicit, but if you want to count coefficients, sometimes it helps to include it. So we use the number 1 to indicate a constant, and then this is just going to be the column associated with that, or the set of columns associated with that. You could equally well do it without the 1. If you, for some reason, you want to express the constant, you put a 0. And then if you had factors, this would be what gets termed one-way analysis of variance. This is two-way analysis of variance, interactions, etc. So to the people using this, this is a way of describing the model. And I find it a very powerful way, especially in teaching, because you don't have to think in terms of the sum of the I go from 1 to n, or all these sorts of things. What I generally refer to as the subscript fest notation. And in many cases you can't get that. So the interaction terms, which we write, it's written in R with a colon, but we know that the colon character is the most overloaded character in the Julia language. So we didn't want to try to put one more interpretation on it. We used the ampersand to indicate that. And when the number of levels are large, we switch to a regularization approach. And in that case, we'll use the vertical bar. So the vertical bar is indicating that you have a large number of levels and you're going to generate some kind of interaction, but it's going to have regularization that's associated with it as well. Because you generally have so many columns in here, but they're generated from indicators, it's an advantage to use sparse matrix methods. So, one of the first things that I did in Julia was I tried to write the formula language. And it's one of those instances, and I've encountered it several times, where, okay, I know how it works in R, I'll start doing, an imitation of how it works, and end up that it gets really messy and really complicated. All right, these things were originally written in C code, using these kind of funky structures and so forth, and I realized, oh, okay, that's just going to get too complex. So recently I went back and I rewrote the whole thing because I've learned a little bit more Julia. I haven't quite got it all down yet, but for some reason the enumeration is supposed to start where this one is up there. So given the set of terms, the first thing that you have to do is you have to descend through this tree, and here those of you that are familiar with symbol manipulation and compilers and all these sorts of things, you can chuckle a little bit, because I'm mostly a numerical person, and so I can manipulate them, but not adeptly. So essentially, I want to go through the abstract syntax tree associated with the right-hand side of the formula, and I want to look for terms of a specific sort, and then I want to find the asterisks in there and expand them. And this expansion can blow up the number of terms. At some point, I'll have to find out from somebody an elegant way of checking, am I currently in a sum when I encounter this multiplication sign? Because then I'll be able to expand to more terms within the sum, rather than the approach that I currently use, which is I generate another sum, and then I do another pass through looking for add of, and collapsing those. I guess Arch has a talk where I was looking at the slides for, and he said that a compiler consists of your code, transform, 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 and machine code. And so, I can understand that approach now. Anyway, you go through and you find the evaluation terms. So those are the things that you have to evaluate. And then for the evaluation term, you have to reduce the data frame, first of all, to the variables that are needed for it. You check for the missing values. You use the desired MA action. You have a series of other operations on there that prepares you for something that you can work with. And this is sort of getting into some of the things that John will be talking about. Then you evaluate those terms, and then you construct all of these others. So there's an interesting multiplication in here, which I don't have a name for. There's times where I have two matrices which have the same number of rows, and I want to generate all pairwise products, element-wise. So I want to take a column from the first matrix, a column from the second matrix, form their element-wise product, and produce the whole, if I start out with P and Q columns, I want to produce P times Q out of that. And then finally, for the random effects terms, there's another operation going on here. The alarm went off, and I actually finished my slides. So this may seem to be very low-level stuff, but I saw another language take off from a meeting of this size to millions of users. And it becomes important to be able to make those users comfortable and also to leverage the power of the language to cut away the gory details and make it obvious to the person what's going on. So the Julia the other optimization, they're doing this, but they're doing it for an intermediate level of user. The engineer might be doing optimization. You don't tend to have, the sociologist coming in to do optimization, but they will have to do some statistical analysis. So the whole purpose of this is to try to make it easier for, it's being recorded, I won't say the great unwashed, for people out there who may not have all the technical chops. It's true. You start teaching these courses, you write a summation sign on the blackboard, and half the class faints. And you have to decide how am I going to teach a technical subject to people under these circumstances. Anyway, thank you.
Questions? Yeah, so I have obviously a very vested interest in all of this myself as well, also having been a long-time R user, and I wholeheartedly agree that the formula interface is one of the best parts of R. What do you think is going to be the capacity going forward? And I know you've been implementing a lot of this anew.
Yes.
I broke your previous implementation. Right. But I broke it because I think in many ways Julia's approach, especially to eval, makes much of what R would do very difficult, which is in R I could write a formula that would look like Z tilde X plus Y, where only, say, Y and Z were in the actual data frame I was manipulating, and X was ambient in the environment from the color scope. I don't really see any mechanism at the moment that we're going to be able to do that in Julia, and so do you think we're just going to bail on that, or do you have another idea of how to go forward?
Yeah, the formula language as implemented first in S and then in R was ambitious. And it was one of these creeping featureism situations that, oh, well, you don't have to put 0 in to suppress. You can put a -1 on the end. And yeah, you can do this and you can do that. And my realization coming back to it is that the features that are used are a very small set. Those other ones were added for very, very special cases, or just because somebody thought, oh, this would be a good idea. And I think it's sort of in keeping with the Julia philosophy of, don't overload with all these bells and whistles. Just, you're going to put it in. It's kind of like Steve, right? With Gecko.
Okay, Daniel.
Danny. Yeah, Danny, sorry. I knew there was a D in that. No, his attitude towards Gadfly is, for the most part, you're going to create a data frame, and you're going to be able to evaluate these expressions in that data frame. So, you have levels at which things are sitting around. It's sort of reminiscent of the lazy evaluation. If you actually look at the implementation in R, it's a nightmare. There is something that's called the standard non-standard evaluation. The term, of course, coming from Thomas Lumley, which is the way that a formula is evaluated in a data frame. Because there's all these optional arguments on the end. So if you look inside a model fitting function in R, the first thing that it does is it turns around and takes the call to its parent, the call to the function itself. And then it strips off the arguments that it doesn't understand in terms of making a model matrix. And then it sends it down to the model matrix, but it sends the environment in which it was called, not the environment in which it's executing. And it's just like, this has the smell of a hack. It really shouldn't be that difficult. And you have to do things like you have to pass along the environment in which the formula was written to be able to make sense of the formula. And this has ramifications as you go downstream. So my expectation is just keep it simple. Don't bother trying to put in every feature that anyone can imagine, because you're just going to end up with Gerbil.
Any other questions?
Yes.
I kind of agree with that, given the question, right, about these things that are out here in the ambient environment cause more pain, I think, when you're writing code for R. And so I come to Julia from R as well, and it's like, dealing with the environments is bad. I think like something that Hadley Wickham's done, where at the very least you're passing in data, and I'm looking at your data, is great because he's using non-standard evaluation. Putting his stuff in functions is a complete nightmare 80% of the time, and which is too bad because they're really useful functions otherwise. So I think if you want to do something, if you want to model some data, that data should be a frame that's getting passed to the call function. It shouldn't be looking at the environment for a random vector that's just sitting out there that you constructed and we're too late to attach to it. Right?
Yeah, well, it gets even trickier because it's not the environment out there, it's the environment in which the formula was defined.
Right, so it's in a function, it's in the calling environment of the function, not the parent environment. Who knows?
This is making things complicated. This is making your life difficult.
It does.